All right, welcome to lecture 21. Today we're talking about nuclear. This is the first video, which always has to do with the resource. Okay, so in discussing nuclear power, we need to always start with a discussion about the atom. So atoms, as you probably learned in like 7th grade, have a nucleus, right, which is made up of protons, which in this lecture I'm just going to leave as open circles. I'll just write pluses for now. And neutrons, which in this lecture I'll write as filled in circles. And then there's little electrons orbiting this nucleus at some distance in orbitals, right? So each atom has a certain number of protons. In this case, this atom, its nucleus has 4 protons. And the number of protons indicates which element it is. Right? So if you have 6, then you have carbon. If you have 1 proton, you have hydrogen. If you have 2, you have helium. Okay? And that gives us the atomic number, which, if you look on the periodic table, is really just the number of protons. And the periodic table, they're all listed in order. Okay, then the atomic mass, the other number on each element, is actually the total weight of an atom. And that accounts for the other particle in a nucleus. So we've got protons, and then we have neutrons. And a neutron is unique because, unlike electrons, which have a negative charge, and protons, which have a positive charge, neutrons have no charge. Okay, so there's something kind of interesting going on, right? So we've got all these particles, protons, and they are all shoved together in a nucleus, and you say, wait a second, opposites attract, likes repel each other. So shouldn't this nucleus be just flying apart in all directions? Well, that's the mystery of the neutron. A proton and a neutron together makes a new particle. I'm sure it's got a name in physics. I don't really know it. But when you have a proton-neutron together, you generate a new force, something called the strong force, the strong nuclear force. And this strong nuclear force holds proton-neutron pairs, and it pulls them towards other proton-neutron pairs. So this strong force is attracting this nucleus so that it is one contained unit. However, the protons are still pushing away from each other, right? So just because they have this strong force doesn't mean they don't still have electromagnetism and want to be repelled from each other. But the strong force is stronger than the force that is pushing them apart. But if you can overcome that strong force, then you can tap into that energy. So because we have a ton of positively charged protons, or just particles really close together in this nucleus, that means our atom, especially its nucleus, contains significant energy. All locked in there, kind of like potential energy or even chemical energy, just waiting to be used if we can figure out how to unlock it. So nuclear energy is another one of those strange ones where its source is not ultimately the sun, right? Tidal power is moon power. Geothermal power is kind of earth power, depending on what kind you have. But then nuclear power is atom power. And honestly, nuclear power is the true power of all the universe because that is what fuels the sun. So even solar power, in the end, points back to nuclear. In fact, the heat inside the Earth is generated from the decay of nuclear, of a nucleus of different atoms in the Earth's crust. So really, I mean, no matter what you do, it all comes back to nuclear power. So this is important. All right, so let's talk about, real quick, radioactive decay. Okay, in order to understand radioactive decay, we need to talk a little bit about isotopes. So you might see things like carbon-12 and carbon-14 and say, well, what does that even mean? So carbon has 6 protons, right? And so you say, well, then it has 6 neutrons. And I would say, well, that depends. If you have carbon-12, then yes, you have 6 neutrons. 12 being the atomic number, right? You count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But then carbon-14 has 2 extra neutrons. Let's make sure I can count and talk at the same time. Yes, I did it. Okay, so carbon-14 has 2 extra neutrons. Okay, these are 2 different forms of the same element, which we call isotopes. Different forms of an element. And the isotope depends on the number of neutrons. Okay, now radioactivity is when an unstable isotope, something like carbon-14, emits various particles until it becomes a stable isotope. So carbon-14 does indeed decay. It has a half-life of several thousand years, I think. And after those years, after it is emitted, in essence, 2 neutrons, it becomes carbon-12, and it's all good. What kind of particles are we emitting? There's 3 kinds. You've probably heard of them. So radioactive atoms are going to emit alpha particles, which are actually the nucleus of helium, right? So it's going to be 2 protons, 2 neutrons. And since these are so big, they don't really travel through anything. It could be stopped by a piece of paper. An alpha particle will not move through a piece of paper. Next, we have beta particles. So a beta particle is when a neutron, which is slightly heavier than a proton, it decays or just turns into a proton plus a neutron. And you say, can it do that? Sorry, a proton plus an electron. And you say, can it do that? And I say, yes. It's kind of just weird atomic level stuff, right? So a neutron turns into a proton and electron, and then it emits that electron. And so the crazy thing about beta particles is if an atom loses a beta particle, that means that its atomic number actually goes up, which is crazy. That means it's gained a proton. It's now become a different element. Okay, finally, last but not least, are gamma particles. These were discovered later because they're really just it's high frequency energy. So we'll call it a high frequency photon, not proton, photon, right? So an electromagnetic particle, and it's emitted as an atom settles. So after it's decayed through alpha or beta particles, there's sometimes excess energy, and that energy is released as gamma particles. Okay. One kind of, I thought, very interesting detail is that radioactive decay is completely random. So if you put a bunch of radioactive isotopes all together and you observe them, you will see that they will all indeed decay over some period of time. The half-life being the amount of time it takes for that amount to decay to half of the number of radioactive isotopes. But there's no way to predict which isotopes will decay and when. All you know is that they will follow some pattern. So it's actually a very kind of mysterious process, to be honest. All right. So that's radioactive decay, but that's not what we're actually using in order to extract energy from a particle. That's a more natural process. But what we care about is nuclear fission. Okay, so in the 1930s, an Italian scientist named I think, is it Enrico or Enrico? I can never remember. Sorry, my handwriting. Fermi. You've heard the name Fermi. So he was bombarding atoms with neutrons, with free neutrons. So let's kind of draw this out as some processes. Let's say we have some stable atom. And then we take a neutron and we shoot it at that atom at a high speed. Well, that neutron is going to impact and join that atom. Okay, so that neutron impacts and it then forms a new isotope. So we still have 3 protons, but now we have an extra neutron. And so this is an unstable new isotope. Because it's unstable, it's going to decay, right? So here again are our protons, here's our neutrons. Our excess neutron right here then is going to decay with a beta particle, which means it emits an electron and leaves a proton. And so we've now caused beta emission by hitting something with a neutron. And so we're going to repeat this until we reach uranium. All right, let's talk about uranium. So in 1938, so here's the important thing about uranium. It is the heaviest naturally occurring element, at least on Earth. If you dig in the Earth, you're not going to find anything except for maybe in trace amounts heavier than uranium. Also, uranium exists mostly as the isotope U-238. But about 1 in 140 atoms is U-235. Okay, now there's something very special about U-235, which Frederick and Irene Julio Curie discovered in 1938. In 1938, they had uranium. So this is not uranium. I do not have time to draw 238 circles. I'm sorry, 235. But just pretend this is U-235. So they just had natural uranium, which would have contained some U-235. And like Fermi, they were bombarding atoms with neutrons. So they bombarded some uranium with a neutron. And then they got really confused because the byproduct was not anything they knew. They said, is this some new atom, something heavier than uranium? But the weird thing is the way they were detecting it to have a much smaller mass, an atomic mass much smaller than uranium. And they said this doesn't make sense. The uranium should have gone up in atomic number. Why do we now have smaller particles? That's because they had discovered fission. So uranium-235 is the only naturally occurring isotope in the Earth that we have, that when you hit it with a neutron, something very important happens. It actually splits into 2 completely different nuclei. So we've generated 2 new ones that are smaller in atomic number, and with those we emit some neutrons. And because we've now repelled, we've kind of somehow broken this strong force and allowed the naturally repulsive force between the protons to happen, we also emit a generous amount of energy as we split this atom. So it's actually a very cool story, but the scientific world came together, they explored this, they figured out that it was indeed fission, that they had split uranium into 2 different things. And so this is fission. And as you can see, this is the way we can tap into all of that energy contained in a nucleus by splitting it in half. Okay, so you can split one uranium, and that's great, but it's not going to power the Earth, right? But if you put enough uranium together, then you have a critical mass, which is the mass of uranium-235 that will result in a sustained or a growing reaction. Okay, so sure, splitting one atom is great, but you want to split enough to get out an appreciable amount of energy. Let's say we have a small mass, less than a value we will call the critical mass, a small mass of U-235. So as we decay, let's say we hit it with some neutrons, and some of those atoms then started to undergo the process of fission, splitting. As they split, they generate more neutrons, and these are going to go and hit other U-235s, right? And those will split and generate more neutrons, and in theory we could have a chain reaction. The problem is we're losing some of those neutrons from our mass. And so for a small mass, you're losing too many neutrons from the surface. And so your reaction dies. You won't consume all of the U-235. But let's say we have a larger mass, right? So now our surface area to volume ratio is smaller. This means that although we will still be losing neutrons, we're not going to lose nearly as many. So if we are above some mass, the critical mass, then we get a chain reaction that is sustained or growing. If it's pure, then it's going to grow, and it's going to grow extremely fast, and you've just generated an atomic bomb. Okay, a couple of notes about fission. Number one, this is a little counterintuitive, but it is the truth, is that if you have low energy, so you can have a low energy neutron, one that isn't moving as fast as a high energy neutron. Well, low energy neutrons actually increase the rate of reaction. To me, this is probably because of a statistical argument. The slower it goes, the more likely it is to hit a uranium atom while inside the critical mass. Okay, and also because U-235 doesn't occur naturally by itself, it occurs mixed in with U-238. So you must refine U-238 in order to get U-235 inside of it, and it's a very inefficient process. Okay, so that's our discussion today about the process of extracting the energy inside of a nucleus through the process of nuclear fission. Really, the only thing you have to do is get a high energy neutron, hit some U-235, and have enough mass of that U-235 so that you generate a chain reaction. Now, we don't want a chain reaction to extract energy at a constant rate. Instead, we want a sustained reaction. So let's talk about some technology we can use to have a sustained reaction of U-235.